All right, section 3.8 is the derivative of inverse functions and logarithms. The hardest part about this is going to be remembering inverse functions and logarithms from algebra. Here's a new derivative rule. The derivative with respect to x of the natural log of a function of x is 1 over that function of x times the differential du dx. Here's the way I remember this rule. The derivative with respect to x of a natural log of some function is going to be du over u. It's the derivative of the argument divided by the argument of the log. So when we're asked to find the derivative right here, y prime is going to be equal to 6 times the derivative of the natural log of 4x is the derivative of 4x over 4x. 4 is the derivative of the argument, that's what that du is, over the argument, that's what the u is. Simplify this, we get y prime is equal to 6 over x. It's just a new rule. Now, what if we don't have a natural log? What if we have a log base a? Well, the derivative with respect to x of e to the x was e to the x, but now if we have a base other than e, it's a to the u, where u is a function of x. It's going to be the exponential expression times the natural log of that base. So here we're asked to find the derivative of y with respect to x. Just use the new rule. Y prime is equal to 13 raised to the x times the natural log of 13 times the derivative of that x, which is 1. Cleaning this up, we get the derivative is 13 to the x natural log 13, and natural log 13 is just a number, it's a constant. This is the derivative of an exponential where the base is not e. Here's the rule for the derivative of a log where the base is not e. The derivative with respect to x of log base a of u is du over u ln a, the natural log of whatever the base is. Essentially, this comes from using the change of base formula in algebra. So we want to find the derivative here of a log base 3. The derivative is going to be the derivative of the argument. What's the derivative of this argument? Derivative of 1 is 0. The derivative of theta ln 3 is ln 3, because that's a constant times your variable. Your variable here is theta. So the derivative is that constant, divided by this argument, 1 plus theta natural log 3 times the natural log of the base. That's ln 3. So when we clean this up, this ln 3 came from the base of 3 right here. Okay, that's from this. And when we clean this up, then we see that we're going to get the derivative is equal to 1 over 1 plus theta ln 3. It's just pattern recognition. Now, why do we care about taking derivatives of logs? Because this is a horrible function to try and take the derivative of. Not only do we have a product rule with a chain rule, with a quotient rule and a chain rule, it's just nasty. But I can use the properties of logs to rewrite this equation so that I have the natural log of y equals the natural log of, this is x times x squared plus 6 raised to the 1/2 divided by x plus 2 raised to the 4/3. Now, if you remember your properties of logs from algebra, you know that you can expand this using the product rule, the power rule, and the quotient rule to make this look like a decent function. So this is going to be the natural log of x plus 1/2 the natural log of x squared plus 6 minus 4/3 the natural log of x plus 2. Now, do you remember the product rule, quotient rule, and power rule of logs? So perhaps I should write them down. Okay, these you need to know as well. They're going to make your life so much easier. If you have a log base a of x times y, you can rewrite that as the log base a of x plus the log base a of y. So I'm using natural logs here. I have a product right there, x times that square root of x. I separated that into a sum of logs. where this is the argument of one log plus the argument of the other log. But I'm using the quotient rule as well. If you have log base a of x divided by y, that's the log base a of x minus log base a of y. So there's the subtraction whenever I was dividing. Subtraction goes with division. And then the power rule is log base a of x to the n is equal to n times log base a of x. So basically what that means is if you have a power in your argument, move that power down front. That makes it easy. Now we can take the derivative, because the derivative of a natural log is just the derivative of the argument divided by the argument. The derivative of the argument with respect to x here is y prime over y. All right, I could say dy dx, but I'm getting tired, quite frankly, of writing dy dx. So I'm going to use y prime. Are y'all okay with that? This is implicit differentiation that we just went over. Equals the derivative of the natural log of x is 1 over x. The derivative of x is 1, and then we put it over the argument. Plus 1/2 times the derivative of the argument is over x squared plus 6. It's the derivative of the argument over the argument. Minus 4/3 times the derivative of the argument is 1 over the argument. Well, now things are going to look kind of nice, aren't they? We're going to end up with y prime over y equals 1 over x plus x over x squared plus 6 minus 4 over 3 times x plus 2. How do I get the derivative by itself? Multiply everything by y. So when I multiply this by y, I've also got to multiply this by y. So what I end up with is the derivative is equal to y, which was x square root of x squared plus 6 over x plus 2 to the 4/3 power times 1 over x plus x over x squared plus 6 minus 4 over 3 times x plus 2. I'm not going to worry about getting a common denominator for this at this point. Just leave it alone. This is what we get. And isn't that much easier than doing the quotient rule with the product rule with a chain rule? From here to here, I wanted to get the derivative by itself, so I needed to multiply by both sides by y. But up here, we said y was equal to this. So that is what I plugged in right here for y. We wrote y as a function of x. That's all I did. This is a theorem that we're going to need in Cal 2, so I'm going to give it to you now. This is the definition, the limit definition of the number e. Find dy dx. All right, let's go for it. This is an implicit differentiation problem. The outside function is the log, and the derivative of a natural log is the derivative of the argument over the argument. The derivative of 4y is 4. I'm going to put y prime. Are y'all okay with that? Instead of dy dx. I'm just tired of writing the dy dx. Over 4y equals, when I take the derivative of the right-hand side, what kind of rule do I have to use? Product rule, along with a chain rule and implicit differentiation. So this is going to be the first times the derivative of the second. You all okay with that? That seems easy now, doesn't it? First times the derivative of the second plus the second times the derivative of the first. And the derivative of e raised to a power is e raised to that power times the derivative of that power. So on the left-hand side, we're going to get y prime over y minus e to the y sine 3x. Y prime equals 3e to the y cosine 3x. What I did was I subtracted this term from both sides of the equation. Subtract this term to move it over here on the left. That way I can factor out my derivative, y prime. So this is 1 over y minus e to the y sine 3x equals 3e to the y cosine 3x. Might want to get a common denominator right here. What are we going to multiply this by to get a common denominator? Y over y. So that's going to give us y prime times, I'm going to show this stuff because I think it'll help, 1 minus y e to the y sine 3x over y equals 3e to the y cosine 3x. Now to get the derivative by itself, we're just going to multiply by the reciprocal. So that gives us 3e to the y cosine 3x, and I'm going to put that over 1 times y over 1 minus y e to the y sine 3x, so that we can tell that the derivative is 3y e to the y cosine 3x over 1 minus y e to the y sine 3x. Can I cancel this y e to the y out? Why not? Because of that subtraction. Very good. And we're done.